we have a question for you, and to encourage you to think of the answer of these questions, I will give each of you, if you try to answer your questions or let others know about your thoughts, then I will give you 0.5 points for the overall scores, no matter this is correct or not for the answers. So the topic is still about what we mentioned, dislocation atmosphere. This is interactions of dislocations and solute atoms, right? So here's the questions. What we mentioned in page 18 is about dislocations attract solute atoms. This is the phenomenon. And the reason is for lowering the free energy, make it stable. And the question is it possible that, in contrast, solute atoms attract dislocations for the same driving force? Right. This is what we just mentioned. The question is it possible in the reverse phenomenon? And so for the background, this is just, I think in previous slide. Edge dislocations will trap both these two types of solute atoms. And screw will just trap interstitial in BCC metals. That's the first one. Second one is, at relative high temperatures, solute atom diffuse faster. And if this solute atom diffuse faster, there will be no dislocation atmosphere, so no interactions. And the third one is, for dislocations in chapter 5, we know that chapter 4 and chapter 5, they can move by two mechanisms. One we call slip, the other we call climb. But for climb, it's actually it's just valid for the edge. So I think that's all you need. So let's go back to this question again. Is it possible that solute atom will attract dislocations? If you think it's possible or not, that's fine. But what's your opinions? What make it possible or make it impossible to do that? Okay, I will give you maybe 3 to 5 minutes. If you have any thoughts, you can raise your hand and share your opinions.
Attract the solute atoms because the solute atoms can diffuse, and during the diffuse, it will be attracted by the dislocation. So, however, if the solute atoms want to attract dislocations, it means that the dislocations may occur slip or climb saw, and this need additional force. So I think it is possible if apply additional force, let the solute atom attract dislocations.
This kind of questions, possible or not, solute atoms attract dislocation for the same driving force. If we do have the same driving force, then what make it possible or make it impossible to attract dislocations? So I think we have heard about the important part for this background, right? For dislocation motions, it must be by slip or climb. But for diffusions, it's different. Anyone? Yes.
Depending on the atomic radius of the solute atom, it can create a compressive or tensile strain. So I think if there's an edge dislocation, it's compressive or tensile, the opposites can attract another.
So you think it's impossible or impossible?
I think it's possible. It just depends on whether the solute is like smaller. Let's say it's interstitial. If it's smaller or larger, it creates a different type of strain. So if it's the opposite of the already existing one, then I think we could maximize that.
Okay, so possible. Anyone?
previous say that the mechanism of dislocation movement and the diffusion is not the same. And we cannot make sure that if these additional atoms is positioned in this alloy. So, and because it will distribute randomly, then this dislocation is maybe, I think it's larger than the atoms, so it cannot attract dislocation to its position because it's comparatively smaller than dislocation.
Oh, okay. So you kind of think of it like a mass difference. So suppose the atom is smaller in maybe lower in mass, and for dislocation is larger.
Yeah.
For this kind of, let's first read this sentence. Interactions of dislocations and solute atoms. So what's the meaning of inter? Inter means these two, they will kind of have a mutual effect on each other. So that's we say interactions. So try to imagine that we have edge dislocation here. This is the slip plate. Then we have compressive strains and tensile strains. What if you have, for example, like a larger diameter of the impurity? For larger solute atoms, it will cause compressive strains. So it will cause C. So let's try to think about it. At the beginning, these two are not binding together. They are separated. So if we can say that dislocations attract solute atoms, it means these solute atoms will be attracted toward the T here, right? So this is about the first case. The dislocations attract solute atoms. How about the question we ask? Is it possible for solute atoms attract dislocations? If these solute atoms attract this dislocation, it means that these solute atoms, it may not move. It could stay there, but for this kind of dislocations, it must move to get closer to the solute atoms. And of course, for the driving force, it's the same. So actually, is it possible or not? It depends on the mobility of these dislocations. If this dislocation can move by slip or climb to get closer to the solute atoms, then yes, it's possible. So let's try to see more about these two cases. So the first case is dislocations attract solute atoms. This is actually what we said in page 18. When dislocations, because they have the strand field, it will attract the solute atoms depending on different types of the solute atoms. So yes, it can attract this. And then when dislocations attract solute atoms, how it happens? So the mechanism is about diffusions, because if dislocations attract solute atoms, then we have dislocation here. This is maybe solute atoms nearby. It must diffuse toward here. So the mechanism is diffusion of solute atoms toward dislocations. Because it is related to diffusions, so we must have at least a certain temperature so that atoms will diffuse faster. And when the atoms, solute atoms, diffuse toward these dislocations, it will create this dislocation atmosphere. The driving force is the same, to lower the free energy. How about the case 2? Is it possible or not? If the solute atoms try to attract dislocations, then the mechanism would be, for example, this is actually the same, but the mechanism is from slip or climb of dislocations. But for slip or climb, if you just put a dislocation there, so you must have a very strong motivation for that dislocation to move. So actually, we have the answers that's very close to the actual answer. That is, it will more likely to occur for this one under external stress conditions. Because if we try to make dislocations to move, then it's about plastic deformation, right? Dislocations to move. So if you have external stress or external force, it will help the slip and climb. That's very similar to the dynamic recovery process. Dynamic, so it's about if you have external stress. So we also mentioned that it's about solid solution strengthening, right? So what's the meaning of solid solution strengthening? So if we have solute atoms, for example, we put solute atoms here. Then we have, actually solute atoms, they are everywhere. So maybe here and here. Then if you also applied a tone to these directions, then this positive edge dislocation will move to left. So this external stress will help dislocation motion, make it easier to move closer to these solute atoms. And when this kind of edge dislocation move close to, for example, these few atoms, then because for lowering the free energies, they will combine together. So it will make it very stable. So what's the meaning of solid solution strengthening? Okay. I think right now you know that both of these two are possible, right? It's just about different aspects and different conditions. So the question is, we actually said, so for example, for this one, tend to shrink or tend to grow, right? So for this one, this is it tend to grow, but it must have two conditions to satisfy. First, more than 6 sides. Second, convex toward the center. So the question is it necessary to does it necessary to satisfy all these conditions? I think so, because let me go back to the origin of these conclusions. We derive those conclusions from the pressure difference. So that's about the pressure difference. So you can think about this as a pressure difference between 2 grains. It means that for 2 different grains, we have 1 grain boundary. And this one grain boundary, we don't know yet if it is stable or not. If it is stable, it means that there is no net force on it. For example, if we have 2 grain A and grain B. If we have a force to right and also force to left, and if both of these two are equal, so there is no net force. No net force. So we can say that for this boundary is stable. But if for this grain boundary, if when you calculate the net force, if you have a value, it means that it's not stable. So it will move toward one side or the other side. So that's the concept for grain boundary migrations. And the number of the grain side or the curvature, they will be related to this delta P. So I think that it must be satisfied for both of these 2 conditions. In other words, we know that, for example, this is n equals to 3 sides, and they have the feature, we call it concave toward the center, so it will disappear, right? It will disappear. So I believe that you will not find a grain looking like this. So it's for this one, this is n equals to 3 and convex toward the center. So I think you will not see this kind of the grains. let's see from the first option. Substitutional solid solutions with smaller solute atoms than host atoms cause a tensile strength field and further interact with edge dislocation. So for the substitutional solid solutions, if we have smaller solute atoms, so smaller solute atoms is the case for left-hand one, right? Smaller solute atoms, so it causes tensile strength. Yes, cause tensile strength. And tensile strength fields you will interact with edge, so this is correct. Substitutional solute atoms do not interact strongly with screw. Yes, that's what we just mentioned, because the strength field is spherical. Substitutional ones do not interact strongly with pure shear. Right, substitutional ones do not interact strongly with pure shear. Okay. How about this one? Interstitial solid solutions with larger. There is a trap here. Interstitial solid solutions. It means that you have impurity. This impurity must fit into the interstitial. It must fit into the interstitial site, right? Fits into interstitial sites. So interstitial solid solution, the impurity diameter must be very small. Must. So if we say that it with a larger solute atom than host atoms, it will not happen. Yeah, so that would be false. Okay, how about this one? Interstitial solute atoms do not interact strongly with screw. Let's just try to check it. Okay, interstitial solute atom could interact with screw in BCC case. So this is also false. This is do not, right? But perhaps I need to change the description here, because this is about do not interact strongly. And actually I don't know about if it is strong interaction or not. So for this description I need to check it better. And I think last one is this one. Substitutional solid solutions with larger solute atom than host cause a compressive strength. Yes, larger solute atoms cause compressive strength and further interact with screw. So this is no, you will not interact with screw. It's kind of related to this one. Okay. So that's just how I made design for that exam sheet. Just to let you know about the concept, not about the equations.